There's basically one predominant method to move a spacecraft.
2, 1. Booster ignition.
Throw something out the back. That might be combustion gases from a liquid or solid rocket, or it might be individual atoms from an ion thruster. But generally, the formula is the same. Take some mass and throw it real hard the opposite direction. Today, I'd like to show you one of those methods, a homemade liquid metal field emission electric thruster. Now, that sounds like a lot of buzzword salad, but in principle, it's a pretty simple device. But as you can see from my numerous prototypes I built, it's been far from easy to implement in practice. Certainly a lot harder than I expected. I spent about 2 months testing 6 or 7 prototypes using 3 different variants of the technology and test fired the device over 150 times. I have about half a terabyte of test footage alone. This project came real close to breaking me, like quit everything and go work on a farm in upstate New York level of burnout. But I finally got it working, and I think it'll be a pretty interesting video. Okay, so complaining done, what are we building? Well, it's a thruster, which is designed to move small spacecraft around. Think like CubeSats or SmallSats. These things don't generate a lot of thrust, something on the order of micro to millinewtons, so you're never gonna launch a rocket with one of these. But they're super efficient, meaning they can accelerate their reaction mass to very high velocities. So once you're in space, these give you a very efficient method to maneuver or gain delta V. Specific impulse is the metric that we care about here. For some context, the Raptor engine that SpaceX uses has a specific impulse around 300, 330, something like that. In contrast, electric propulsion methods have specific impulse anywhere from 1,000 to 10,000. FEP, the thing that I'm building, usually clocks in around 3,000 to 9,000. The fuel is a liquid metal, usually indium or gallium, and it's drawn up a sharp tip by capillary action in an intense electric field, typically on the order of 7,000 to 10,000 volts. At the end of this tip, the electric field is so strong that it starts to pull the metal away from the tip itself. This forms what is known as a Taylor cone. It's a dynamic balance between the surface tension of the liquid trying to keep it adhered to the tip and the electric field trying to pull it away towards the extractor electrode. If the potential difference is large enough, the very end of the cone forms an apex that is only a few nanometers wide. Here the field is so concentrated that individual metal atoms begin to ionize and are ripped free from the cone. This field-induced emission of ions is often just called field emission in the literature, but confusingly it's not the same thing as field emission where electrons are emitted from a sharp tip, like used in some electron microscopes. So, I don't know, scientists are just bad at naming things sometimes. Anyway, once free, the ions are attracted by the extractor electrode and achieve huge velocities, on the order of 20 to 40 kilometers per second. Since these are fired in vacuum, the ions don't collide with anything and are simply ejected out the back. And that's how it works. By accelerating and ejecting the ions, you can generate a tiny amount of thrust, but do it very efficiently. It's a very commercialized technology too. There's a well-known company called Impulsion that makes a variety of liquid metal FEP thrusters for actual use in space. Anyway, that's enough background for now. Grab your favorite beverage, buckle up, because we're gonna start building some prototypes. And frankly, I really have no idea how long this video is gonna be. It could be a minute. There are 3 main variants that have been studied in the literature, categorized basically how the liquid metal gets to the tip. There's capillary, externally wetted, and porous emitters. My first prototype used a porous emitter array made from sintered glass. This is basically the glass filters you might find in like a chemistry lab, but CNC machined to generate the spikes. The idea is that once saturated, these small pores in the material help efficiently wick propellant up to the tips. Impulsion uses this technique, but they use sintered tungsten for their emitters instead of glass. This entire project came about because a few years ago, I machined some glass emitters for Michael Breddy over at Applied Ion Systems. Michael is an amazing engineer that has been working on a variety of different electric propulsion modules, everything from vacuum arc thrusters to micro Hall effect. He reached out asking if I could machine some of these porous glass emitters for an ionic liquid electrospray system that he was building. This uses a different propellant, an ionic liquid, but it's a very close cousin to liquid metal thrusters. Anyway, ever since then, I've been enamored with both electrospray and field emission and wanted to build my own. Since I knew how to machine these glass emitters already, I figured that'd be a good place to start. So I machined up an array and began trying to load it with propellant. I chose to use tungsten, which is a mix of gallium and indium. Unlike the two pure metals individually, this alloy is liquid at room temperature, so I won't need to use heaters to liquefy the metal. It just makes logistics a little simpler for me. Tungsten is really quirky stuff though. Like on one hand, it's super reactive and will wet out most materials. But on the other hand, it forms a thin skin of oxide almost immediately. And this oxide has incredibly high surface tension. To actually wet out a material, you have to puncture this oxide skin, which ends up being really challenging. For example, it's relatively easy to coat a glass slide. You just rub the tungsten around a little bit and you end up wetting it out. But it's almost impossible to do the same for a porous glass emitter I found. You can't rub the tips because they're too fragile, and the trapped air inside of the pores prevents it from infiltrating any deeper. I tried a few methods to wet the array, and none of the techniques I tried were particularly safe, so we won't be showing that footage. The best I could do was a partial wetting, where some of the surface and a few of the tips were coated. I figured I was probably good enough to at least test it, so I made up a Teflon base, then a second electrode was aligned over the top of the tips, and it was placed inside the vacuum chamber for testing. We pump down to 2 × 10⁻⁵ millibars and begin applying high voltage. Not a whole lot happens as the voltage is slowly raised until suddenly we get a bunch of fireworks. And then nothing else. The device seems to have died. But how cool is that, right? I mean, this was my first attempt and the results looked super promising already. I tried reloading the propellant a few different times, but it quickly became clear that the porous glass array was probably not the right approach. There's some prior art in the literature, and it seems like most people use extremely high pressures to force liquid metal into sintered glass. And the sintered tungsten folks do it under high vacuum and high temperature. Neither of those seemed like a lot of fun, so I decided to explore some of the other variants instead. I ended up building 3 types of capillary thrusters and 2 types of externally wetted thrusters. But the development timeline is really confusing since I kept jumping around between all the different prototypes as my frustration grew and my mental wellness kind of slowly evaporated. So I'm gonna rearrange some things in the edit to make it a little more coherent. But if you happen to see like the test stand or whatever changing in the background, just know that it might not be entirely chronological. So the capillary type thrusters use some kind of enclosed tube or wall structure to wick the metal upwards. The first one I built was called an annular slot thruster. There's basically an inner section and an outer section which are separated by a very small slot. I machined this prototype out of stainless steel and then carefully lapped the inner diameter so that the 2 parts are separated by a 12 micron gap. The outer section is bolted down, precision shims are placed around the circumference, and then the inner section is secured in place. The shims are 12 microns thick, so in theory we should have an equal spacing all the way around. In practice, the slot varies a little due to manufacturing issues on my end. It ranges from 9 to about 30 microns depending on location, but I figured that's probably acceptable. Gallium is loaded into the reservoir at the base and then assembled with the electrode on top, and it's into the vacuum chamber for testing. The first few tests were really energetic, but not necessarily in a good way. Unfortunately, I don't have much footage of this because apparently this thing puts out so much electromagnetic interference that it corrupted the video files on my camera's hard drive. I have 3 recordings that are completely corrupted, and I think it actually ate a few unrelated clips that were just sitting on the drive. Once I realized this, I switched to using an internal SD card, which seemed to fix the issue, but not an expected problem to have. The main issue with this design is the bridge section between the inner and the outer electrode. Because it's directly over the slot, the electric field is highest here, and the gallium prefers to emit from that location. It also sometimes spews out droplets, which then connect to the bridge and shorts the top to the bottom, which effectively ends the test, and you have to vent it all to atmosphere to fix. I tried reducing the size of the bridge. Here it's only 0.5 millimeters wide, but it still was too big and we had the same problems. So eventually I removed the inner electrode entirely. The impulsion thrusters actually only have an outer ring, so in theory it should work. I tried a ton of variations in the size and the distance and thickness and just could never get it working. Either the electrode was too far away and nothing happened, or it was too close and would start to arc. The arcs look really cool, but it's not stable emission or anything and doesn't actually generate thrust. It's just fireworks. Although at one point I did accidentally make an LES, a light emitting screw. This was both hilarious and terrifying at the same time. The screws are nylon, which is a good insulator, but it's also very hygroscopic. Under vacuum, nylon slowly outgasses water vapor. And I guess it had outgassed enough that kind of the local area around the screw became sufficiently conductive that it could form a plasma. So yeah, that was exciting. My final iteration on this was to put the central electrode back, but connect it by a long wire instead of bridges. So this should hopefully avoid the bridging issue, because there's nothing directly above the slot anymore, but keep the field strength high by having both an inner and an outer electrode. Unfortunately, I couldn't get this to work either, for much the same reasons. Either nothing happened or it would start to arc. Okay, so annular slot thrusters are known to be relatively finicky to get working. So let's back it up and try something just a little simpler so we can get some kind of prototype working. This is a spike array for an externally wetted variant. It's a lot like the porous array we tried earlier, except it's solid instead of porous. So basically there's the same set of pointy spikes, and the liquid metal clings to the outside of the spikes and is drawn upwards along the external surface by capillary action. Coating with metal is challenging here too, but a little easier than the glass. Gallon stand just kind of sucks to work with, honestly. I found the easiest way to coat it is to put it in a chamber with some hydrochloric acid fumes, which helps accelerate the wetting process. The fumes dissolve and help prevent the oxide from reforming on the surface of the gallon stand. And this helps the liquid metal wet out other metals a lot easier. With some additional mechanical encouragement, I got most of the spikes covered. Then the spiky spatula nestles into a PTFE base, gets capped with another piece of PTFE, and an array of extractor holes. And you know the drill by now. Into the vacuum chamber, pump it down, and ramp the voltage for testing. This variant turned out to be very unstable. I tended to get big bursts of activity and then nothing at all. Since the spikes are all kind of in the same cavity, I think even the smallest arc or emission would generate enough plasma to lower the conductance inside the chamber. And then that would trigger more spikes to emit, and the effect would kind of cascade across the whole array. If the spikes were loaded with too much gallium, sometimes a blob would fly off and short out the array. I tried a variety of hole diameters and spacings and, just could never get a stable configuration to work. Not to worry though, the engineering department here at Breaking Taps is full on ADHD. So let's go work on those slot thrusters again. There's a variant that's much simpler than the annular thruster, and that's just a single linear slot. It's the same thing in principle, but it's much simpler to manufacture and ensure a consistent spacing. One side is flat, and the other has a reservoir for propellant and a very shallow passage for the liquid metal to flow in. The two halves are carefully lapped so that the gap is only 10 to 12 microns wide, and the whole thing is assembled. It's loaded into a PTFE fixture, and it's vac chamber time. This setup happened to find a whole bunch of unrelated logistical issues. There was arcing between the aluminum test stand and the wire. I fixed that with some Kapton tape and better spacing, but then there was arcing between the thruster back and the Kapton tape. At one point, the insulation on one of the magnet wires just totally came off.
I don't know how well this shows up on camera, but the insulation on the wire started to arc inside the vacuum chamber, and I realized the vacuum pressure had dropped 2 orders of magnitude.
So I machined a full PTFE backplate and swapped the wires over to peak insulation. But like all the other thrusters, this one suffered from excessive arcing. It was made worse by the aspect ratio over the extractor electrode. Because it was so long and thin and unsupported down the middle, it would actually flex towards the emitter. Once it would get close enough, it would arc, the force would temporarily vanish and the electrode would spring back up to the top, and then the process would repeat. It basically started vibrating at really high frequency. Okay, so not gonna lie, around this point I was strongly considering quitting and just throwing everything into the ocean. This whole project was supposed to be an easy diversion from the bird robot project. I had recently let the magic smoke out.
Yep, that's not good. Oh no.
And hadn't really worked up the willpower to get started again. I was hoping to just knock out a cool little plasma thruster and then get back to work on the robot. Instead, it's been like a month of pure frustration. Each prototype takes a few days to design and machine, and then each test cycle is a minimum of an hour or two waiting for the vacuum chamber to pump down, run the test, and then vent back to atmosphere. Then more time to review the footage and debug what went wrong before setting up the next test. It's been a long month. However, I am more stubborn than I am smart, so I decided to just keep going and make a new design. One that, honestly, I should have started with from the beginning, a single capillary emitter. This is how the first original thrusters were made. They use small metal needles, but I opted to use thin glass capillaries because they can be pulled to a very sharp tip to make micropipettes. I even have a pipette puller, but of course, when I pulled it out of storage, it decided to stop working. I don't know, I think like the transformer died or something. This thing is probably older than I am. But not to be deterred, I hooked it up to a big DC power supply and just controlled the temperature manually. It's all sorts of janky, but it got the job done. Once pulled, the capillary is cut down to size and filled with gallium. You can actually pull tips that are crazy small, like only a micron or two wide. These are used in electrophysiology all the time as patch pipettes. But at some point, the pressure required to fill it with gallium gets so high that you just explode the capillary. So there's a practical limit to how small you can make it. A nice feature about these glass capillaries is that they're entirely insulating, except for where the gallium pokes out the top. This should, in theory, help prevent arcs and accidental shorts. I also changed the filming setup so that we could get a really close-up view for debugging purposes. And boy, I am glad I did that. Check this out. Okay, first of all, I think we can appreciate just how cool that looks, right? I wish I had it in slow motion, but even at this frame rate, like, wow, that's really cool. To be clear, this isn't working at all. This was an abject failure of a test. But diagnostically, this was huge. First, we can see the liquid metal being pulled towards the extractor, and then we can see some Taylor cones starting to form on the surface. Then there are blasts of plasma erupting from those spots. There are also very obvious droplets shooting around and landing on the electrode. So the process is almost working, but we're generating big droplets instead of controlled ion emission. We can also see an issue here that I've been suspecting for a while, the oxide skin. In a different clip, there's a very obvious skin of oxide that's resisting the formation of a Taylor cone. Remember, I said the oxide has a really high surface tension, and so it's going to take more voltage to form a Taylor cone than fresh gallium. Eventually, it explodes outwards and is replaced with fresh, shiny gallium. Because this is in vacuum, that oxide skin doesn't reform, which means the new gallium has a much lower surface tension and is far more likely to form a Taylor cone. So my working hypothesis is that the tests are going over voltage due to that oxide skin erupting, and then the excess voltage, it starts ripping whole droplets off of the fresh gallium. This would explain a lot of the behavior we've seen so far in the tests. Around this time, I was talking to Michael at Applied Ion, and he suggested adding some current limiting resistors. By limiting how much current can jump between the electrodes, we should hopefully control the arcs and prevent that droplet formation. Honestly, I should have thought of this sooner. My power supply has a current limit on it, but I guess it's just not fast enough to tamp down on pulses from arcs. And I don't know, I suck at EE, so this isn't very surprising. So I got some 1 mega ohm high voltage resistors and tried again. The results were not perfect, but encouraging. On multiple tests, I managed to get a very faint blue glow and no droplets or arcs, which is fantastic. I'll take that any day at this point. The glow is gallium plasma that's being extracted from the capillary. Now the trick is just to increase that glow and make it more stable. I tried to reduce the aperture size, but this brought back some arcs and shorting, and I wasn't able to get it stable at a larger aperture. I decided I needed a sharper tip than I could get with the capillary tubes. I thought sharper tips would reduce the onset voltage because, the sharper you get it, the more intense the field is at that location. I later learned this really wasn't the case for ion field emission, but oh well, that's what I did at the time. So I etched some tungsten wire electrochemically, like I did in the DIY image sensor video. These were then coated in gallium and test fired. And some Tentative success. We can see the gallium blob moving around on the spike.
Oh, is that it? I think that's it.
And then it starts to glow from the sides. A bit of gallium can start to be seen building up on the edge of the aperture as well. If we shift the camera position a little bit, we can see the glow is actually a tiny little plasma spike.
There it is. How about that? Just the cutest little plasma plume. Oh man, it's adorable. Look at it. It's so cute.
That's it. That is exactly what we wanted. I let this run for a few minutes and it seems stable. I could also turn on and off the power and basically turn on and off the plasma as well. You have no idea, no idea how much relief I felt at this point. After so much work, we had finally found some success. Of course, I couldn't really stop there. I want to know how much thrust this was generating. To do that, we need to start using a Faraday cup. Basically, this is a big copper cap that's connected to a pico-ammeter. The ions hit the cup and generate a current, which we can read out. Then we make some mathematical assumptions and we can get a value for the force. So, how much force was this generating? Well, of course, it's not going to be that easy, is it? Nothing's ever that easy. After getting the Faraday cup set up, I just couldn't replicate the plasma. It would not relight again. I also let the magic smoke out of a whole bunch of resistors while testing, which is, to be fair, my fault. They aren't actually rated up to 10,000 volts like I thought, so they had a habit of dying on me. I ordered some new resistors and began working on the last major problem, getting the gallium to nicely coat the spikes. Gallium is sitting on these tips, but they aren't really wetting out correctly when you look closely. It's full of holes and there's lots of oxide junk kind of sitting around. The tests that worked may have just been a lucky fluke. Another issue is the surface roughness of these tips. The electrochemical process makes a very sharp tip, but it also makes a very smooth tip. And apparently, from reading the literature, you need a certain amount of roughness to help wick metal up to the very top. This is done usually with some kind of chemical etching agent, but those are really quite gross for tungsten. So I decided just to start making these on the belt sander. It's almost as sharp as the electrochemical approach, but leaves a nice rough surface. Incidentally, focused ion beam microscopes use a gallium ion source with basically the same structure, a sharp tungsten tip. So how are those made, you ask? Well, the tungsten is heated to a white hot heat in ultra high vacuum and then dunked in gallium, which has also been heated and allowed to react for a while. And I don't know, that sounded like a lot of work. So how about a blowtorch instead? It took some fiddling, but if you make sure the tip is entirely submerged in the gallium blob and then torch the whole thing until it glows, that usually works. It forms a really nasty crust on the outside of the gallium, but when you pull the tungsten out, it will have a nice clean coating. Then we pop it into the vacuum chamber and finally we can get some good measurements. Got a test running in the vacuum chamber right now, and I thought I would give you just a little tour of how the whole setup is, how it's set up. And you can see this is basically it. Forgive the messiness. It kind of evolved and yeah, it's not great. But so we've got the chamber here, obviously. The test stand is on the inside, aluminum extrusion. The thruster under test as the Faraday cup, which is used to collect current. Got a camera monitoring it. Turbomolecular pump controller there. Valves, etc. Turbo pump. This is the high voltage feed through with a kind of a custom Teflon and copper connector because it didn't come with one. And then over here we've got some electronics. There's the vacuum pressure gauge, the high voltage power supply, and can't really see that because of the glare, but that is a pico ammeter, which is going to a feed through right there. And that's being used to collect the current or measure the current from the Faraday cup. And then obviously lights, camera, and a display showing everything that's happening on the camera so I can keep an eye on things. It's not quite as pretty as the earlier one, but it's very stable, and I've relit it a few times cycling in and out of the vacuum chamber. Current on this one maxed out around 114 microamps, which if we run the numbers, this works out to around 11 micronewtons. This includes a few assumptions like beam divergence and ion charge and ignoring any secondary electrons generated at the Faraday cup and stuff like that. But as a rough measurement, it should be pretty close. So there you go. 2 months of work and I've generated about a milligram of force. Other than the gallium coating issue, I found that the spike was much happier with a 100 mega ohm resistor. Seeing that the spike liked a higher resistor, I decided to retry the glass capillary and found it actually worked really well with 50 mega ohms of resistance. But thrust is just one of the measures, and I was curious what the efficiency, the specific impulse was. To do that, we need to measure the mass before and after a test fire so that we can calculate the mass flow rate. The spike unfortunately just doesn't really carry enough propellant to measure easily with my equipment, so I loaded up a capillary, masked it, and ran a test for 30 minutes. Afterwards, we can calculate the change in mass, and from that, the specific impulse. This test run actually came out to 15 micronewtons of thrust and about 3,100 seconds of specific impulse, which is, it's pretty mediocre for a thruster of this variety, but not at all awful comparable to like a chemical thruster. And, for a DIY thing, I'm happy. I haven't revisited the array or slot designs yet, but I think I could probably get them working by carefully tuning the current limiting resistor. In retrospect, I think a lot of the arcing problems I was having was just from the lack of having a resistor there. There seems to be a sweet spot where enough current flows to maintain the plasma, but not so much that it generates arcs or droplets. That said, I think the spike arrays and slots will be harder to keep stable just because any differences in, manufacturing or assembly of the different tips or section of the slot will change the onset voltage of that location. And if you get one starting to fire, it'll affect how the other ones are firing, and I think it'll just be a more challenging problem. So what's next, you ask? Well, as noted earlier, this is a lot like a focused ion beam microscope. Historically, FIB is actually a descendant of space thrusters, which is cool. I always thought it was the other way around, where the microscopes came first, but actually it was the work on the liquid metal capillary thrusters that led to the tungsten-tipped emitters, which then went on to be used for the ion beam microscopes. So, I don't know. I thought it was just kind of cool that like a space application ended up building this whole new field of ultra-precision micromachining and microscopy. It's just neat how stuff like that works. Anyway, I could continue to refine the setup, add a bunch of ion optics, and make a really low-quality focused ion beam microscope. That seems kind of cool. Or alternatively, I've worked up some designs for a better space thruster. There are features like serpentine pathways to prevent short-circuiting from the sputtered material and like a focusing electrode to improve the thrust and, just better logistical manufacturing layout. I don't think I'll touch any of this anytime soon. I'm super burned out on it, but maybe someday. No sponsor this week, so if you'd like to support this channel, I have a Patreon. I usually write a monthly write-up about what I'm working on, and recently started doing video updates with additional context and footage. This video, for example, generated so much footage and side tangents that there's no way it's going into the main video on YouTube. I always tell myself I'll make like a secondary engineering cut video with more details, but it never happens. I've said that like 3 or 4 times now. So I'm gonna start using Patreon as an outlet for all of that technical detail just so it can land somewhere other than my notebook. Okay, I think that's all I got for you. I hope you enjoyed it, and I'll see y'all next time.